Here's the Chapter 20 homework problems discussion and going over. And as I said in class, I recognize these were, I'm sure, very challenging for us based on how quickly we're heading into it and the amount of background we've had and so forth. So I would encourage you to look at your 5 steps to a 5. I think Chapter 11 has some stuff with this. Go back and look at the conceptual questions, my lecture notes, stuff like that. All right, so problem number 7. This is a plastic ball that's been rubbed with a wool stick. Actually, that's not true. Those are questions. Problem 7 says 2 identical metal spheres A and B are in contact. Both are initially neutral. 1 times 10 to the 12th electrons are added to sphere A, and then the two spheres are separated. Afterward, what's the charge of A and what's the charge of B? So I've got an extra 1 times 10 to the 12th. That doesn't show up very well. Electrons, I shoved them here, touched, and then separated them apart. So half that amount, or 5 times 10 to the 11th electrons, will be on each sphere. And that's assuming they're the same radius. It actually doesn't matter if they're the same type of metal or not, but it does matter that they're the same radius. So we've got that, and then we do the conversion factor, which is on your formula sheet on the side with conversions and metrics and stuff like that, of 1.6 times 10 to the negative 19th coulombs per electron. And since electrons have negative charge, I put that in. So that says that negative 8 times 10 to the negative 8th coulombs of charge on each sphere. So that's negative 80 nanocoulombs. So that was a kind of a straightforward thinking about how the charges will be split and then converting from fundamental charges into coulombs. For problem 14, it was said a small plastic sphere with a charge of negative 5 nanocoulombs is near another charge with a charge of negative 12 nanocoulombs. Actually, did I do that right? Okay. Oh yeah, the spheres repel each other with a force of magnitude 8.2 times 10 to the negative 4th newtons. What's the distance between them? So this is a Coulomb's law problem. So I know the force. I know the Coulomb's law constant, so that's K, not epsilon sub 0, which is vacuum permittivity. I don't know the distance between them, but I know the charge on each one. I'm not concerned about the positives and negatives here. In fact, if you look at the version of the formula on your formula sheet, first of all, they annoyingly have 1 over 4 pi e epsilon 0 instead of K, but also they show absolute value here. And what that means is you can determine whether the force is attractive or repulsive. Not that big of a deal. So anyhow, I rearrange this, solve for r squared, that's my r squared, that's my r. That's about an inch or 2.57 centimeters, but again, we always would think of things in standard units, so it's 0.0257 meters. For problem 24, what we've got are it says a bumblebee can sense electric fields as the field bend hairs on its body. That's actually really cool. Bumblebees have been conclusively shown to detect an electric field of 60 newtons per coulomb. Could a bumblebee use this to sense or detect the presence of another nearby bumblebee? So suppose a bumblebee has a charge of 24 picocoulombs. How far away could another bumblebee detect its presence? Okay, so this is an electric field problem. Now, we're going to treat the bumblebee as a point source. So for a point source, I'm going to go to formula E3, which looks like this. But remember, all this is basically just K. So it's really this formula. Let's see if I can do that. Oh, that's exciting. Look at that. That's really this formula right here. Swoosh it. Okay, so I know the constant. I've been told what the charge is, 2.24 picocoulombs. Well, that converts to that many coulombs. You're going to get really good at doing conversions in your head with metric things this year. And that equals the field strength, E, of 60 newtons per coulomb. So we have to solve for R. So when I do that, I get that that's 0.06 meters. So yes, up to 6 centimeters away, so that's a little less than 3 inches, a bee can detect another bee, which is actually kind of interesting. It can do that electrically. Maybe you felt that where you've been charged up on a carpet or close to lightning where the hairs stand up on your arms. Like, that's a weird feeling. Okay, problem 29, and unfortunately I kind of finished it on the next page. I got squooshed and I did not do a good job thinking about that. So I guess I'll put those together. So problem 29, there's a picture, and it looks like this. I've got a positive charge here, positive charge here, each of 1 nanocoulomb. So that's 1 times 10 to the negative 9th coulombs. 5 centimeters each from the center line, and then there's a point which is 5 centimeters to the right of that. So what it's asking in this case is, what is the strength and direction of the electric field at this position? So hopefully that Fed activity kind of helped you visualize this. But electric field lines point away from this, and electric field lines point away from this. But the field is a vector quantity. So at this point, the vertical components of the lines pointing away from these charges cancel out, but the horizontal components will add up. So really the first thing I need to do is figure out what is the overall electric field at that point caused by one of these charges. And then I can actually use symmetry and geometry to help me figure out the net electric field. So I'm going back to this formula again, which is formula E3, or a version of it. K, Q, because it said this was 1 nanocoulomb, over R squared. Well, why did I use 0.071? Well, that's because this was 5 centimeters and this was 5 centimeters. This hypotenuse is the actual distance of the charge from that point. So 0.071 meters. So when I do that, I get the electric field at this point is 1785 newtons per coulomb caused by this charge. Obviously, it would also be 1785 newtons per coulomb caused by this charge. But the vertical components of those fields cancel out, whereas the horizontal components would add up. And this is how, again, I got the 0.071 meters. So I know that this is a 45-degree angle from each of these charges to here, because I was given that each side was 5 centimeters. So to find the horizontal part, I would take that electric field and multiply it by the cosine of the angle to determine the horizontal component. So 1785 newtons per coulomb times cosine of 45 degrees gave me that amount of field horizontal from the top charge. Well, now I know that from the bottom charge, the vertical part of the field will cancel out, but the horizontal part won't. And since it's the same amount of charge and the same distance away, it would have the same amount of horizontal electric field that's created. So therefore, 1260 times 2 gives me 2520 newtons per coulomb. So I visualized it like this a little bit better. So this is still part of 29 up here. Okay. For 33, I'm using formula E9. That is shown in the chapter, so if you go to the section with capacitors and things like that, or part about talking about capacitors, which might be even a little later in the chapter, it says that a parallel plate capacitor formed from 4 times 4 centimeter electrodes are spaced 2 millimeters apart. The electric field strength inside is a certain amount, 1 times 10 to the 6th newtons per coulomb. What's the charge on each plate? Well, at this point, you just simply have to go back to this formula. You know the charge on each plate. You know you can determine the area of each plate. This is a constant, and you know the electric field. So really what you're going for in this case is to find the amount of charge. So there's this constant. There's the field strength you were given. The area is 0.04 times 0.04 meters, which I believe gives me 0.00016 square meters. So when I do that and I rearrange it algebraically, I get 14 nanocoulombs, or 1.4 times 10 to the negative 8th coulombs. So note here that the space between the plates doesn't matter. The electric field is going to be the same whether or not those plates are close together or far apart. All that matters is how closely packed those charges are to each other. For problem 35, what we have here is being asked, it says again it's a parallel plate capacitor. It's constructed of 2 horizontal 12 diameter circular plates. A 1 gram plastic bead with a charge of negative 6 nanocoulombs is suspended between the two plates with a force of electric field between them. So which plate, upper or lower, is positively charged? So let's think about that a minute. If we have a positively charged or a negatively charged bead, so I'm going to go here and make a negative. That is weird. And I'm going to get color other than white. Let's have blue. So something like this. This is a negative charge. So if that's a negative charge in there, a negative 6 nanocoulombs, normally, if there's any mass to that charge and it said there was 1 gram, it would accelerate downward in the absence of air resistance at 9.8 meters per second squared. But it's not accelerating downwards. So what I can do to help me is I want to go back to thinking about free body diagrams. You remember those from first year physics. So if this is suspended here, that tells me that the gravitational force down is exactly balanced by the electric field that's up at the top. So if I have an electric force pointing up, if I have an electric force acting on a negative charge, that's got to mean that this plate on the top is positive and this plate on the bottom is negative. So that helps me. For part B, in order to figure out the amount of charge on each plate, I really got to find this electric force. So now I'm going to find the electric force because I know it's equal to the gravitational force. So that's the mass of the bead, that's the gravitational acceleration. You could also use 10 newtons per kilogram. And so that is the force down. So the electric force up has to be this. Well, the general formula for electric field under all conditions is it's a ratio of electric force to amount of electric charge. So that's the amount of force I just calculated. This is the amount of charge that I was told. And therefore, this tells me the field strength. 1.6 times 10 to the 6th newtons per coulomb. So now, if I know that charge, I know this vacuum permittivity. If I know the area, I can figure out, or pardon me, I know the electric field, vacuum permittivity, and area, I can figure out the amount of charge. Well, I do know the electric field strength because I just got that. I do know this constant. What about the area of a plate? If I go back up here, it said that the circular capacitor plate is 12 centimeter in diameter. So that's a 6 centimeter radius, so that's 0.06 meters. So the area of a circle is pi r squared. So pi times 0.06 squared is 0.0113 meters squared. That goes down here. So literally I've got every piece of information I could need except the charge, and that's what I'm trying to solve for. So this is the answer. The book answer, for whatever reason, forgot to put a negative exponent. That would be a ridiculously high number of coulombs. So the correct answer is 1.6 times 10 to the negative 7th coulombs. Okay. 37 and 51. This is basically saying you're outside. There's storm clouds up here. This is a hill. And it's asking you to draw out the electric field lines and the charge locations. So the charges are going to pile at the tippy top of that, and that means that the electric field in this region is going to be very strong. And so that's why it's more dangerous to be at the top of a hill. You get those charges piling up on the ground, no matter what's happening in the clouds. You get a strong electric field, and again, you would feel tingly at this point if you had a pretty strong electric field. Kind of like the bumblebee. Hey, the code word for this is, the code word for this screencast is kicker. It's kicker. So if you can come in and tell me the code word for this screencast, I will get you a donut. Just seeing if anyone listens, because there was a lot to this. All right, we're going to finish off with 51 and 68. So problem 51 says two equally charged 1 gram spheres are placed 2 centimeters in between their centers. When released, they each begin acceleration at 225 meters per second squared. What's the magnitude of the charge on each one? So this, despite the fact that we're in year 2 physics, goes back to Newton's second law, the all-master physics equation, which is really true. So it's A equals F net over M tot, so force over mass. I can rearrange that. If I know the acceleration and the mass of the spheres, I can figure out the net force. So be careful because it gave the mass in grams. I need to make sure that's kilograms. So I converted it, so it's 1 times 10 to the negative third kilograms each. And therefore I get a net force of 0.225 newtons. So now we can use Coulomb's law. Since we know the net force, these two charges are going to be equal to each other, so it's kq squared over r squared. And I can use that to find the charge. So the charge on each of those 1 gram spheres is going to be 1 times 10 to the negative 7th newtons. So note that we are ignoring the gravitational attraction between these because it's ridiculously small. And you might say, well, wait a minute, 0.225 newtons isn't much. It's not, but this is 0.000000000000167 times 10 newtons, something like that. I might have been off by a 0. So gravity is completely negligible compared to the electric force. Number 68, cut this off over here. So I said this is similar to AP questions and the last page of the sticky tape lab. So for my cohort B, we just did that in class earlier today. So this is your second shot at this. So we've got 2 3-gram spheres, each on the end of a 1 meter light string. They're 40 degrees between the two. The midline's down here, so they're each 20 degrees from the midline. So what your goal is to figure out the charge on each of these spheres. So what I'm going to have to do is think about the forces that are involved. I know that on each sphere the gravitational force acts down, and the electric force is acting horizontally is a repulsive force. So, keeping that in track, the gravitational force, mg, 0.0294 newtons, and notice that this tension counteracts both gravity and electric forces. So that's not really important for what we're doing here, but it's useful to understand why this thing might not be accelerating. It's connected to a string. So here, if I know that the electric force is horizontal and the gravitational force is vertical, and I know this angle, I can say that the tangent of 20 degrees is equal to the ratio of electric force over gravitational force. And if I've gotten the gravitational force, which I did up here, then I can figure out the electric force. So as it turns out, the electric force here is 0.011 newtons. All right, so, this then, 0.011, 0.0107 newtons is the electric force. So now I can go back, put it into Coulomb's law, do an algebraic rearrangement. Again, I think we did this in class. Solve for the with the force here equal to k, the q squared, the distance between them squared. So in this particular case, the way that I figured out that distance between them was actually that if this is 20 degrees and this is 1 meter long, then this distance is going to be 0.34 meters, so the distance between them has got to be 0.68 meters. I actually did that early because I knew I probably was going to need to use that trig somewhere else. So that's where the 0.68 meters came from in terms of the distance between these two spheres. And that should do it. That gets me a charge of 7.4 times 10 to the negative 7th Coulomb. Sorry about such a long video, but remember, that's the kicker.